All right, so let's take a look at allylic carbocations and how we can explain their interesting behavior in light of what we just learned about conjugated systems. So let's start with electrophilic addition reaction because that has a carbocation intermediate. If I start with an alkene, react it with HCl. Here, I'll redraw the H and the Cl there so we'll get used to its mechanism. The pi electrons will attack the H. That will displace the bond between H and Cl, so we'll end up with a carbocation plus chloride. The carbon that became attached to the hydrogen is determined by where the more stable carbocation is formed. So that's why I bonded the H to the end carbon as opposed to the interior carbon, because bonding the H to the end carbon gives us this more stable tertiary carbocation, which can then be attacked by the chloride ion to give us the Markovnikov product. Right, we've done that before, that Markovnikov regiochemistry, where the nucleophile ends up on the more substituted carbon, all comes from that carbocation stability. If I do this with a diene that is non-conjugated, I'll end up with a similar type of compound. Okay, we just will have added two chlorines into it. Right, one of them will attack the H and we'll end up with a carbocation there. The other one will attack an H and we'll end up with a carbocation on that internal carbon. That'll give us these two chlorides now, both of them in Markovnikov positions relative to the original starting alkene. So non-conjugated alkenes react in exactly the same way as just a regular single alkene would. Now, if I have a conjugated diene, and I react it with something like a strong acid, HBr, HCl, something like that, instead of just getting the single Markovnikov product, we will get two products. Okay? We'll inevitably get a mixture of products. So the first product that we have here just simply results from attack these pi electrons here on the H, giving us a carbocation. Let's draw that carbocation intermediate. ch14 now. Right there. Okay, we have a secondary carbocation, just like that. Now, if the bromide that's left over just attacks that carbocation as is, we get a normal Markovnikov type product. Okay, this ends up being 3-bromo, 1-butene. We haven't touched that other double bond yet. We've just added an H and a Br across the other double bond. This is referred to as a 1-2 addition. And it's very important you realize whenever we say 1-2 addition, we're not talking about the IUPAC numbering. Okay? We're not talking about how we would number this compound, because we would number this one starting with the double bond over here. No, a 1-2 addition simply refers to the two things that were added in an addition reaction and their relative relationship to each other. So whenever you've added two groups just on adjacent carbons, that is a 1-2 relationship. Okay, we've performed an addition that's added to adjacent carbons. So if one of those happened to be carbon 1, the other would be carbon 2. Okay, but remember, 1-2 relationship is not talking about how we've named the molecules, just the distance of those two added groups from each other. The other thing that happens, though, we end up with a different product. Okay, and let's just, before we talk about how this comes about, let's analyze what actually happened here. We have a CH3 on the end, just like before, so there's one addition. But now the bromine that was added is on the other side of the molecule. So this is called a 1-4 addition. The bromine and the H are a 1-4 relationship. Okay? If one of those were attached to carbon 1, the other would be attached to carbon 4. Turns out that is how we actually name this compound. But the other interesting thing that's happened here is that we've migrated a double bond. Okay, where we started out with double bonds between 1 and 2 and between 3 and 4, we now in our product have a double bond in the middle between 2 and 3. So there's something interesting happening in the mechanism here. Let's analyze it to make sure that we are able to figure this out. That first carbocation that I formed right here on this secondary carbon, it is actually an allylic carbocation. So don't forget what allylic means. When something is allylic, it is next to a double bond. So when I have an allylic carbocation, I have two important resonance structures. Right? The pi electrons can move over. Okay? I can do a pi to pi transition. So doing that, well, the pi electrons will be moving towards the positive charge that will satisfy this positive charge, but then leave the vacancy on the other end of it. So remember, we've always talked about resonance structures happening in groups of 3 atoms. Right? Here are those same 3 atoms here, where the plus was originally on one end of the 3, in the other resonance structure, the plus will be on the other end of those 3. And remember, resonance structures are not 2 different isolated structures. They're just 2 views of the same thing. So the actual structure, if we could envision it, would look something like this, where I would have still that CH3 on the end, but now sort of half double bonds on those 2 end ones, and sort of half positive charges distributed between carbon 1 and 3 because of those 2 resonance structures. Okay? Both of those are equal to that hybrid. So just for reference here, this where we've formed a primary carbocation, where I've attached the hydrogen on the second carbon end, this is not formed for 2 reasons. The carbocation is primary instead of secondary. Also, the carbocation is no longer allylic. Okay? It is not next to the double bond. There's another carbon between it and the double bond. So we're not going to worry about that one. That primary non-allylic carbocation is not formed. So we have extra driving force for the carbocation to be on this second carbon in, because then it is conjugated with that other double bond in there, and we end up with this resonance structure. So as a result then, of course, the bromine can attack either one of those partially positive structures. So what I can do now, I can draw the other resonance structure as that, okay, where the double bond has migrated it in. We now have the plus charge on the end, which the bromide can attack, giving this other product. Just remind ourselves, this is the other resonance structure of the carbocation intermediate of this reaction. So if I have a unsymmetrical conjugated diene, I can actually produce a maximum of 4 products. Okay? 2 of those will come because either one of those double bonds can start the process by attacking a hydrogen, and then we multiply that by 2 again because each of those has 2 resonance structures. So let's take this one part at a time. I have cyclohexadiene, okay, conjugated, so I've got 2 double bonds within the 6-membered ring, but I have a methyl group on carbon 2. So 1 and 2 is a double bond, 3 and 4 is a double bond, carbon 2 has a methyl group on it. So now it's become unsymmetrical. If I didn't have that methyl group, we would have our normal 2 products just from the resonance structures. But to figure this out, let's just go one at a time. I'll start with this double bond, attack the H, displace the chloride, and draw the resulting carbocation. 6-membered ring, methyl group, retain that other double bond between carbons 3 and 4, We originally had one H on carbon 1. We now have two H's on carbon 1 and a carbocation, now a tertiary carbocation on carbon 2 where that methyl group is. Okay? We do that because it's more substituted than the secondary one and because it is allylic, so it has a resonance structure. Remember, you can't move any atoms in resonance structures. You can only move electrons. So these two pi electrons, here, let's use a green arrow for that. The pi electrons will move towards the positive charge, and it will invert that allylic carbocation. Just like that. Okay, so there is one pair of resonance structures. Remember, these both represent the same thing, but now a bromide ion could attack either one of those. To give two different products. One with the bromine on the same as the methyl group, one with the bromine way down on carbon 4 after the double bond has migrated. Okay, so there are two distinct products so far. But let's go back. Let's consider this other double bond attacking the hydrogen. Now, 3 and 4, those are both going to end up as secondary carbocations, but the H will only attach to carbon 4 because that'll give a carbocation on number 3, which will be allylic to the double bond. This compound, I'll do the carbocation on 3, retain the double bond on 1 and 2. It will have a resonance structure where the double bond will move towards the plus charge. Just there, double bond down there. But look at these two structures. They are equivalent by symmetry. I have a methyl group in the middle of the 3 carbons representing the allylic carbocation. Okay? In both cases, I have a double bond going one way and a plus charge over to the other side. So both of these will yield, right? Since these are essentially the same thing by symmetry, they'll just yield only one additional product. This one right here, and I'll just take the first one there. But bromine on carbon 3 with the double bond retained, which is the same as bromine on carbon 1 with the double bond migrated to 2 and 3. Okay? Those are the same because the methyl group is still in the middle of them. So that is our third product. So depending on the symmetry, there could be as few as 2 or there could be as many as 4. This one has 3, it turns out, products. So in order to tackle a problem like this, just take each double bond, draw a carbocation immediately where it would make it allylic, and then draw the resonance structure of that, attaching the nucleophile to both locations. Some cases, due to symmetry, both of those will end up as the same product. In other cases, you'll have different products. So follow that general format and you should be fine. Oh, I just see that I added bromine in all these cases. Let's just pretend this was HBr in the first place. Right? But it works just the same with HCl. Okay? Any strong acid will have the nucleophile that adds into the carbocation. So there we go. Problem solved. Now, the reactivity of the 2 carbons in that allylic carbocation can actually be explained by the molecular orbital diagram. of the allylic carbocation. So let's just start with butadiene. Okay. Let's react it with strong acid. That'll give us an allylic carbocation, right, which has 2 resonance structures. Like that. This carbocation in either resonance structure must occupy an empty p orbital. Of course, the double bond contains p orbitals that has the overlap, but that carbocation has to be in an empty p orbital because we cannot change hybridization when we're doing resonance. All we can change is where electrons are going. So I have a pi system which consists of 3 p orbitals that are adjacent to each other, 3 isolated, right? Remember we already do this, 3 isolated p orbitals can interact in one of 3 ways. Let's just draw the lobes like we did before. Remember, lowest energy will always have all overlapping. Highest energy will always have all destructive, right, with nodes in between each of them. So that means the middle one must just have one node right on the middle. So no electron density occupying the center, and then opposites for those ones. The bonding on the bottom, the anti-bonding on top, the non-bonding in the middle. Just the same energy as we originally started with. Now, notice in this pi system, there's a carbocation and a double bond. That means there are 2 pi electrons occupying these 3 orbitals. We're going to fill the orbitals from the bottom, so that means 2 electrons will occur down in the bottom. Those 2 electrons that are there will equally be occurring throughout those 3 p orbitals. The lowest unoccupied molecular orbital is the lowest energy place that can accept electrons or a pair of electrons, okay, donated from the nucleophile. And this should make sense because if we were to put something in this lowest unoccupied molecular orbital, we would be filling p orbitals on carbons 1 and 3, nothing on carbon 2. So that partial positive charge, right, this lack of electron density, will mostly be occurring in carbons 1 and 3, not in the middle one where there's a node. So that ends up being the place that can accept electron density. We confirm that by calculating this electrostatic potential map. Carbons 1 and 3 have a good amount of partial positive charge to them, where carbon 2 does not.